Imagine for a moment you're at the helm of a massive, maybe multi-billion-dollar new high-speed rail project.
Wow. Yeah.
Cutting-edge trains, sophisticated signaling, miles and miles of new track, billions invested, millions of passengers eventually relying on it every single day.
Huge responsibility.
Absolutely. Expecting flawless on-time journeys. But here's the burning question. How do you, with absolute statistically proven certainty, ensure that every train, every signal, every little component won't just work on paper?
Right, in the design phase.
Exactly. But will perform reliably day in, day out for decades, facing all the real-world challenges. It's about building, an unbreakable trust, isn't it?
It really is.
This is exactly where RAM comes in: reliability, availability, and maintainability. It's not just about designing robust systems. It's about proving that performance, before the first passenger even steps aboard.
That's absolutely right, because no matter how brilliant the design is or how meticulous the engineering in the lab might seem, nothing truly verifies its accuracy and completeness like real-world operational experience. You can model everything, simulate endlessly.
Yeah, run the numbers.
But until that high-speed train is actually out there, facing the elements, extreme temperatures, constant vibrations, the relentless operational cycles, you just don't truly know its full capabilities.
Right.
So today's deep dive isn't just theory. We're going to explore the essential, rigorous methods used for successful RAM demonstration, bridging that really critical gap between what's promised on paper
and what's actually delivered.
Exactly, what's delivered in the field.
So our mission today is really to unpack the critical processes and methods used to demonstrate RAM in these railway projects.
Yeah.
We'll explore exactly how engineers and project teams verify that these incredibly complex integrated systems meet their demanding performance targets after they're built, installed, and, put into operation. We're talking about proving, with hard data, that your multi-billion-dollar high-speed rail line is genuinely ready for prime time.
And this isn't just for the seasoned project managers or the chief engineers out there.
Right.
Whether you're an engineering student maybe grappling with system design or an early career professional navigating the complexities of large-scale infrastructure projects like our high-speed rail example, or even just a railway enthusiast who's curious about the unseen efforts that keep those trains running smoothly and safely.
Yeah.
This deep dive will give you a foundational understanding of how that critical confidence is built, how it's proven, and, importantly, how it's continuously maintained.
Okay.
It's really about transforming raw operational data into actionable decisions that impact, everything from safety to your morning commute.
Okay, let's unpack this then. Before you can even begin to prove anything about your high-speed rail system's reliability or availability or maintainability, you need one absolute non-negotiable ingredient: solid, consistent data. Think of it like a doctor trying to assess a patient's health without any vital signs, no medical history, no lab results. You're just flying blind.
Yeah, exactly.
An effective data collection process, often called RAM monitoring, is the absolute necessary condition for everything else that follows in RAM demonstration. It really is the lifeblood of the entire project.
Absolutely.
Yeah.
And while data collection might sound, deceptively simple.
Yeah, just collect the data.
Right. Its implementation in these gargantuan railway projects, like our high-speed line, can be shockingly difficult to implement effectively.
Why is that?
Well, because you're dealing with a multitude of stakeholders, each with their own systems, their own data formats, sometimes even their own definitions of what a failure actually is. You have the client, the railway owner. You have main suppliers for the trains, the signaling, the power supply, and then countless subcontractors for specific components. I mean, everything from the HVAC on the train to individual track circuits. So defining a unified data framework that everyone can actually stick to, and then ensuring the quality and consistency of that data across dozens of different companies. It's a monumental challenge.
I can imagine.
It's often where projects stumble before they even get to the analysis phase.
So this is where a very important and maybe often unsung hero comes into play: FRACAS.
FRACAS
Stands for Failure Reporting, Analysis, and Corrective Action System. And it's truly the central nervous system for achieving RAM performance in any complex system, especially one as intricate as a high-speed railway.
That's a great analogy, central nervous system.
Yeah. The core purpose of FRACAS is to systematically report both software and hardware failures.
Right.
Once that raw data is collected, it then drives the identification, implementation, and most importantly, the verification of corrective actions. The ultimate goal is always to prevent, or at least significantly reduce, future failures. Ensuring those trains keep moving safely and on time.
Yeah. And it's really crucial to understand the life cycle perspective here. This directly impacts our high-speed rail project.
How so?
Well, the options for corrective actions and the flexibility you have to implement them are overwhelmingly greatest during the design and manufacturing phases.
Ah, okay. Early on.
Exactly. Imagine if we discover a design flaw in the braking system software during initial testing of our first prototype high-speed train.
Right.
We can fix that software code, test it, update the design specs for all the subsequent trains, often at a relatively low cost, and without really impacting the project schedule significantly.
Makes sense.
However, if that same fundamental software flaw is discovered after, say, 50 trains have been manufactured and are already in revenue service carrying passengers,
oh boy,
your options become incredibly limited. A recall of the entire fleet for a software patch, or maybe even a hardware retrofit, it would be astronomically expensive.
Yeah, huge disruption.
Massive service disruption, potentially significant reputational damage. So this really emphasizes why FRACAS isn't just about reacting, it's about early intervention. But it continues to be vital throughout the entire operational life of the system to catch issues as they emerge.
So what does a comprehensive FRACAS process actually look like on the ground? Let's say for a critical subsystem on our high-speed train, like the door mechanism.
Okay, good example.
It typically encompasses 4 essential steps, right? The first is event reporting.
Yeah.
And this is far more than just a quick note saying door broke.
Definitely not.
It requires an exhaustive, almost forensic level description. What exactly were the symptoms the train driver or passenger observed? Did the door just not open? Did it jam? Did an error message pop up?
All those details.
What were the immediate effects on the system or service? Was the train delayed? What was the precise date and time? Where exactly did it happen? Specific station platform, a particular train set ID, maybe even a specific door number.
Crucial details.
And crucially, clear identification of the affected item using part and serial numbers for traceability.
Yes.
So not just the door, but train set 101, door 3, motor assembly XYZ, serial number 12345. Why this level of detail?
Well, without it, you can't track recurrence. You can't identify faulty batches from a supplier or link the failure back to specific repair data. It's absolutely paramount for any effective investigation that follows.
Okay, so step 1 is detailed reporting. What's next?
Building on that precision, the second step is problem investigation. Every single failure event, once reported in detail, triggers an investigation.
Right.
And this has to happen at both the software and hardware levels. The immediate failure cause is determined first. That's what the repair team initially observes and diagnoses on site.
Okay.
For our door example, it might just be door motor jammed.
Seems straightforward.
But, and this is a really critical distinction, the immediate failure cause is not the root cause. Think of it like that doctor analogy again. They might treat your symptom, like a cough, but their real job is finding the underlying illness causing the cough.
Gotcha.
Similarly, in railway systems, an in-depth analysis and investigation are required to find that true root cause, the fundamental issue that led to the immediate failure.
So why did the motor jam?
Exactly. Was the door motor jammed because a bearing failed due to insufficient lubrication? Or because a software glitch sent a conflicting signal? Or maybe vibration on that specific train set caused a wire to fray? Without addressing the root cause, that door motor will likely just jam again. This often involves techniques like fault tree analysis or the 5 whys method, digging deeper and deeper until you hit the true origin of the problem.
Okay, root cause identified, then what?
Once that elusive root cause is known, we move to the third step. Corrective action identification. This is where an action plan is defined, with the primary aim being to eradicate or significantly reduce the failure mode's probability.
Right, fix it properly.
So if our high-speed rail door motor problem was traced to an undersized bearing, the ideal corrective action would be a design change. Use a larger, more robust bearing.
Makes sense.
However, And this is the practical reality for a live high-speed rail operation. Sometimes the full design change just isn't feasible or affordable for systems already in operation.
Yeah, recalling 50 trains.
Exactly. Imagine trying to recall all 50 high-speed trains to replace every door motor. In such cases, the goal shifts from complete eradication to mitigation.
Okay, so damage control.
Sort of. We might introduce a palliative measure, maybe a temporary fix or a workaround, to make the failure effects acceptable, even if the root cause isn't fully eliminated by a design change.
Right.
Perhaps it's a new maintenance schedule to lubricate that bearing more frequently. Or maybe a software update that allows the driver to override a jammed door more quickly. The key here is that once a corrective action is implemented, its effectiveness must then be demonstrated. You have to prove it actually achieved its intended purpose.
Verify the fix worked.
Precisely. You need to verify that your fix actually fixed something.
And that verification leads to the final step.
It leads directly to the fourth and final step in the FRAC-S process. Problem closure. After a corrective action has been implemented, its effectiveness isn't just assumed.
Right.
It is formally validated over a specific observation period. This isn't just a casual check. It could involve monitoring that door system for a certain number of operating hours or maybe hundreds of DIRT cycles to ensure the failure mode doesn't reappear.
Okay.
Or if it does reappear, that its frequency or impact has been significantly reduced. Only after this validation period, and with confirmation that the action has indeed been effective and the problem is truly resolved, is the problem formally closed within the FRAC-S system.
Wow.
And this entire process, from that initial detailed event report right through to final closure, requires a defined data framework and robust workflow management, often achieved through specialized commercial tools or maybe in-house systems.
To keep track of it all.
Exactly. To ensure complete traceability of every single reported issue throughout the entire life cycle of our high-speed rail project.
Okay, so once that rigorous FRAC-S process is in place and data is starting to flow, and we're talking massive amounts of detailed information flowing in constantly from every train, every trackside system.
Yeah, it's a flood.
A crucial next step is defining exactly what data to collect. This brings us to the parameters of interest. You called it the art of choosing the right data.
It really is.
It's a real dilemma, isn't it? On one hand, you need enough detail for thorough investigation and proper data processing for RAM analysis.
Right.
But on the other hand, if you ask for too much detail, it can lead to poor data quality, missing info, or just overwhelming the people collecting it in the field.
It's a very delicate balance. You absolutely have to find that sweet spot.
How do you find it?
Well, to guide the selection, you have to ask key questions. And these are often debated heatedly in project meetings.
Like,
things like, are all the items being monitored under the same operational conditions? For our high-speed rail, are we looking at trains running in tunnels versus open air lines? Big difference.
Yeah.
Do we need to characterize the item by its specific application conditions, like the climate zone it operates in? Does failure responsibility matter for classification? Who's accountable, manufacturer or operator?
The blame game.
It can be, yes. Is a failure only relevant if it's proven to be a hardware fault, or do we also capture software glitches, human errors? The answers to these questions profoundly impact what data you need to ensure meaningful analysis.
So context is everything.
Absolutely. A parameter that might seem irrelevant when testing a single component in a nice, clean factory could become absolutely vital when monitoring a complex railway system operating across diverse environments.
Can you give us a really tangible, real-world example of this? Something that clarifies why getting the right parameters matters so much.
Certainly. Let's stick with our high-speed rail and think about trackside signaling equipment. Maybe a specific type of sensor that detects train presence.
Okay.
For overall system reliability design, maybe environmental factors like extreme temperatures or heavy rain seem broadly covered. The sensor was designed for those conditions, right?
You'd think so.
So you might not think to record them with every failure. However, if your goal is to demonstrate the reliability of these sensors specifically when installed in tunnels compared to those exposed to direct sunlight and heavy rain on open air lines.
Okay, now it matters.
Suddenly those environmental parameters become absolutely vital. A sensor on an open air line getting baked by the sun, higher internal temperatures, may be constantly drenched in rain. It might exhibit significantly poorer reliability performance compared to an identical sensor deep inside a tunnel.
Stable conditions.
Exactly. Stable temperatures, controlled moisture. If your data collection doesn't differentiate for these environmental conditions, you could end up with incomplete data.
Leading to bad conclusions.
Precisely. inaccurate conclusions about the reliability of specific components in specific environments. You might wrongly blame the sensor itself when it's actually its application environment that's stressing it beyond its limits. It's a very nuanced but critical point for accurate RAM demonstration.
So how do you categorize these parameters typically?
They generally fall into three main categories for a system like our high-speed railway. First, we have operational data.
Okay.
These are the data points that describe the application conditions, and they're independent of any specific failure events. They provide crucial context.
Like?
Things like the working ratio, the percentage of time an item actually powered on. That helps define its actual operating hours, which is vital for MTBF calculations.
Right.
It also includes environmental factors. Is the item in an air-conditioned compartment? Does it have forced ventilation? Is it exposed to direct sun? Ambient temperature range, humidity, even the intensity of mechanical stress from train movement.
Wow. Okay.
All of these are crucial for understanding the context, for investigation, and for traceability if you need to compare performance across different scenarios.
So that operational data gives us the backdrop, but the real action happens when things go wrong. That's the event data, right?
Precisely. The second category is event data. This is information meticulously collected when a failure occurs.
Okay.
It includes the exact event date and time, the specific project phase, commissioning, testing, revenue service, and a clear, concise description of the circumstances and consequences.
But what happened?
Exactly.
Yeah.
For our high-speed rail, this would include the precise location kilometer marker, station ID, train set ID. Critically, also, the symptoms the user observed, what messages appeared, what did the driver see or hear, how was passenger service impacted.
Delay data, too.
Oh, absolutely critical. Delay data directly caused by the event is huge, and it can be tied directly to contractual definitions and potential penalties. Even seemingly small details, like whether an emergency brake was applied, can be relevant event data illuminating the severity.
And finally, once the fix is underway, what kind of information is collected there?
That's the third category, repair data. This information is vital for enabling the investigation and classification of the failure's true nature and ultimately its root cause.
Okay.
This category includes detailed notes on the repair activity itself, the repair diagnosis defining the technical cost, specific repair actions taken, like component replacement, software reset, mechanical adjustment, whether the repair is scheduled preventive maintenance or an unscheduled corrective fix, and the responsible repair unit manufacturer team, field service crew, local depot.
Got it.
All of these parameters across those three categories are carefully defined based on the specific needs of our high-speed rail project and the level of detail needed for accurate RAM demonstration and continuous improvement.
Okay, we've talked about collecting all this rich data through fracas, but data alone isn't enough, is it?
Not at all.
Who acts as the ultimate arbiter, the decision maker, when it comes to classifying a failure, assigning responsibility, driving corrective actions? Who makes sense of all that information?
That brings us to the Failure Review Board, or FRB.
FRB.
The FRB is truly a cornerstone of effective RAM demonstration, especially on a project with as many interfaces as a high-speed railway. Its roles are quite extensive.
Such as?
Reviewing failure sentencing, basically. Formally classifying a reported event as a chargeable failure against a supplier or not.
Chargeable. Key word.
Very key. Arbitrating any disputes over failure responsibility, which is particularly common and important between a client and a supplier.
I bet.
Supervising the entire RAM performance monitoring process to ensure it's effective, data quality is maintained, and most critically, making strategic decisions related to in-service reliability and maintainability demonstration.
So it's the decision hub.
It's the forum where the raw data collected through fracas gets formally reviewed, debated, and then, crucially, acted upon.
So it's not just a single meeting. This sounds like a pretty high-level ongoing process managing a lot of potential friction.
It absolutely is. And the FRB typically takes place at different levels, not just between the final client and the main train or signaling supplier. Subcontractors may also attend FRB meetings when failures involve their scope of supply, which happens all the time in complex railway projects.
Makes sense.
In fact, it's often recommended that additional sort of subsidiary FRBs be set up between main suppliers and their subcontractors to manage issues at lower tiers before they escalate.
Okay.
The main FRB is generally co-chaired by senior representatives from both the client and the primary supplier. They meet regularly, often weekly or bi-weekly, to review failure data.
And they need to come prepared.
Oh, meticulously prepared. These aren't ad hoc chats. Both parties arrive with clear positions on the chargeability of each failure, backed by investigation reports and data. Based on the trends shown in failure analysis reports, the board decides on the priority for RAM improvement actions and assesses the effectiveness of actions already taken. This is where raw data truly transforms into actionable decisions that influence the system's performance and impact the project's bottom line. I once saw a project where a key piece of equipment was reported as failed every single Tuesday morning for weeks.
Every Tuesday. Weird.
Right. The FRB kept reviewing it, trying to find a technical flaw. Turns out, it wasn't technical at all. The cleaning crew was accidentally hitting the emergency stop button during their routine.
No way.
Yeah. Without that deep dive into the parameters of interest and the FRB's persistence in investigating, they'd have chased a phantom technical bug for weeks. It's all about context and collaboration.
That's a perfect example of why this board is so critical. Okay, so we've collected the data, we've analyzed it through FRACUS, the FRB is making decisions to drive improvement in our high-speed rail project. But how do we actually prove that our system hits its reliability target?
Right, the proof.
It's not enough to just say, yeah, we think it's reliable. You have to demonstrate it with statistical rigor.
Exactly.
This is where the statistical demonstration tests come in.
Precisely. The goal of reliability demonstration tests is to formally demonstrate the achievement of specific reliability targets, whether that's during the development phase of a new component or once it's already in operations.
Okay.
This typically involves testing a sample of items, meticulously observing any failures that occur, and then analyzing the collected data to estimate and formally demonstrate its reliability.
So testing a sample, watching for failure.
Yeah. And while early testing, on prototypes can provide the greatest benefits at minimum cost.
Catching issues early.
Right. Saves massive money down the line. But RAM demonstration is very often required once systems are already operational, which presents its own unique challenges.
Right.
Most common methods focus on demonstrating a constant failure rate, which is basically equivalent to demonstrating a mean time between fault or MTBF, since MTBF is just the inverse of the failure rate.
Okay, MTBF. Got it.
And for these tests, we usually assume that failed units are replaced immediately, so the test can continue keeping the system operating.
Okay, let's start with what sounds like the most straightforward approach. Fixed duration tests. This is probably the traditional way, right?
Yes, this is a very common and foundational approach. The setup is quite clear. We want to statistically prove that the observed MTBF of our system, or maybe a critical component like a specific traction motor, exceeds a specified target. To do this, we consider a design MTBF, let's call it theta 0.
Theta 0.
This is the MTBF value the producer or designer aimed for, essentially building in a margin. For our traction motor, maybe it's, say, 20,000 operational hours.
Okay, the target.
Then, from the consumer's perspective, that's you, the railway operator. There's a minimum acceptable MTBF, which we'll call theta 1.
Theta 1, the minimum.
Right. This is the absolute lowest MTBF you're willing to tolerate for that motor, say 15,000 hours. The producer designs for FATO, which should ideally be comfortably greater than FATO.
So ARRI is the ideal, what the manufacturer aims for, and ARRI is the absolute minimum acceptable for the operator. And the ratio between them is important.
Correct. The ratio ARRI divided by ARRI is called the discrimination ratio. It's always greater than 1, and it represents the producer's margin.
Okay.
A higher discrimination ratio indicates a larger margin, meaning the producer is very confident. And as we'll see, it generally means a shorter test period is required for given levels of risk, which is a big advantage in a tight schedule.
Right. Shorter tests, good.
Now, in these tests, we establish two hypotheses. The null hypothesis is that the true MTBF is greater than or equal to. Essentially, the system is good meets the design target.
System is good, H0.
And the alternative hypothesis is that the true MTBF is less than or equal to AIR, meaning the system is bad, falls below the minimum acceptable.
System is bad.
H1. The entire test revolves around deciding which of these hypotheses to accept.
And how do you make that decision in a fixed duration test? What's the rule for our traction motor?
The acceptance rule is based on a predefined total test duration, T. We also set a failure threshold, denoted C.
T and C.
The rule is simple. If the number of observed failures, K, during the test period T is less than or equal to C, then H0 is accepted. Test passed.
Okay.
For example, if we test a sample of these motors for a total of, say, 10,000 hours and set a threshold of 2 failures, if we see 0, 1, or 2 failures, the test is passed.
Simple enough.
However, if K exceeds C, say we observe 3 or more failures, then each is rejected, test failed. It's a very clear pass-fail criterion, like a quality control check, run a batch, count defects, pass or fail.
That makes sense intuitively, but in any statistical test, especially with high stakes like our real project, there are always risks, aren't there? You could make the wrong decision.
Exactly. This is where type I and type 2 errors, or what we more commonly call producer's risk and consumer's risk, become absolutely paramount.
Producer's risk and consumer's risk, okay.
The producer's risk, also known as a type I error, denoted by alpha, is the probability that the test fails. You observe more than C failures, when in fact the true MTBF of the system is actually greater than the design MTBF.
So you reject a good product.
Exactly. It's the risk to the producer of a false negative. Their good traction motor is wrongly rejected. That could lead to costly retesting, redesigns, maybe even loss of contract.
Ouch. Okay, that's the producer's risk. What about the other side, the risk for the railway operator?
That's the consumer's risk, or type 2 error, denoted by beta.
Beta.
This is the probability that the test passes you observe no more than C failures, when in fact, the true MTBF of the system is actually less than the minimum acceptable MTBF.
Ah, so you accept a bad product.
Right. The risk to you, the consumer and operator, of accepting a faulty or underperforming product, a false positive. You get a motor that seems fine in the test, but then fails prematurely and frequently in service.
Leading to delays, costs.
Delays, maintenance costs, reputational damage. Understanding and agreeing upon these risks, alpha and beta, is absolutely paramount for both parties to ensure fairness and acceptable levels of uncertainty.
So how do you actually determine the test parameters, that minimal test length T and the failure threshold C, given these acceptable risks and MTBF targets? Sounds complex.
It is, but thankfully, it's an iterative process often done with established tools or tables. Given your desired values for ER, and beta, the goal is to find the minimal test length T and the threshold C that satisfy these risk levels.
Okay.
This often involves using tabulated results, which are basically pre-calculated tables based on statistical distributions like the Poisson distribution.
Like a recipe book for tests.
Kind of, yeah. A recipe book for reliability tests. You tell it your acceptable risks and targets, and it gives you the optimal test duration and failure threshold. They're built on rigorous statistical models to ensure fairness and efficiency.
Do you aim for equal risks, alpha and beta?
Ideally, yes. It's generally desired to have I and but be equal to ensure a shared risk level. But it's not always perfectly achievable in practice because failures are discrete counts. But these tables provide the closest approximations.
Okay, so what does this all mean for project timelines? Fixed duration tests can be quite long, right? Especially for high reliability stuff.
It can be, yes.
This is where sequential testing comes in, aiming to shorten the duration and make decisions faster. Is that right?
That's precisely the motivation. The core principle behind sequential testing is efficiency.
Right.
If, in a fixed duration test, you've observed a number of failures that clearly exceeds your threshold much earlier than the planned end.
Why keep going?
Exactly. It doesn't make sense to continue testing. You've already got enough evidence to reject. Similarly, if a system performs flawlessly for a very long period, you might have enough confidence to accept it sooner. Sequential tests allow for these earlier decisions.
Saving time and money.
Saving time and money for our high-speed rail project.
Yes. How does it actually work in practice, say, for our new signaling system?
Well, the decision rules for a sequential test are typically plotted on a failure time graph, usually as 2 parallel lines, an accept line and a reject line.
Okay. Visual.
As the test progresses, you accumulate operating time and observe failures. You plot these points on the graph. As soon as the observed failures cross either the accept line or the reject line,
test over?
Test is terminated, and a decision is made accordingly. So if your new signaling system starts having frequent failures early on, boom, you hit the reject line quickly. If it performs exceptionally well, you hit the accept line.
So the test duration isn't fixed?
Exactly. It's determined by when enough evidence is accumulated.
That sounds like a great way to save time and money, but if the duration isn't fixed, couldn't it theoretically go on forever if the results just hover between the lines?
That's the key trade-off and a valid concern.
Yeah.
Yes. While sequential tests are generally shorter on average.
On average.
Their duration cannot be predicted in advance. Theoretically, the cumulative failure count could just wiggle along indefinitely between the accept and reject lines. No decision ever made.
Not good for a multi-billion-dollar project.
Absolutely not. You simply can't afford that kind of uncertainty. To counter this, A truncated sequential test is usually adopted.
Truncated, meaning?
It means a maximum test time or a maximum number of failures is defined as an upper bound. This ensures the test will eventually conclude, even if a clear decision isn't reached earlier by crossing the lines.
Ah, a safety net.
Exactly. The design of these tests involves determining the discrimination ratio, calculating the constants for the accept-reject lines, and computing these truncation points, often using something called chi-square tables, another set of statistical tools to manage probabilities.
Now, let's talk about a seemingly simpler alternative that some clients might push for, something called the chi-square confidence interval test method.
Yes, that one.
It sounds straightforward, right? Just look at a confidence level. But you warned, there's a hidden trap.
There is.
This seemingly straightforward method can quietly shift a massive amount of risk onto the supplier, almost like signing a contract without reading the fine print.
That's a very good way to put it.
It's the kind of statistical blind spot that can cost millions, right? A critical point for anyone involved in these high-stakes contracts.
You've hit on a crucial point. While seemingly simple and appealing, this method is actually quite deceptive and potentially very dangerous for suppliers.
Why? How does it work?
It's based on the statistical relationship between Poisson and chi-square random variables. This allows a confidence interval for the MTBF to be derived from observed failures over a total test time t.
Okay.
The appeal comes from two things. First, it avoids that discrimination ratio, which some clients find unfamiliar.
Right.
Second, it uses the more familiar concept of confidence level, like 95% confidence, rather than explicitly talking about producers' and consumers' risks.
Seems easier to grasp.
It does. The method works by observing interiors over an operating period, T, calculating a lower bound for the confidence interval of the MTBF, let's call it MTT flow.
Okay.
The hypothesis that the true MTBF is greater than a target MTBF is then accepted if, and only if, MTT flow is greater than that target. Simple comparison.
Looks simpler, easier to understand. So what's the catch? Why should our high-speed rail operator or supplier be wary?
The critical warning here is that even though producers' and consumers' risks don't explicitly appear in the calculation, they absolutely still exist implicitly.
Hidden risks.
Exactly. And crucially, this method often leads to asymmetric risks, with the producer's risk being much, much greater than the consumer's risk.
So it's biased against the supplier.
Heavily biased, often. This is the statistical blind spot you mentioned. Imagine a manufacturer building a critical power converter for the train. It perfectly meets its contractual MTBF target, what they agreed to deliver.
Right.
But because of this asymmetric risk inherent in the chi-square confidence interval method, they might fail the test repeatedly.
Even with a good product.
Yes, forcing them into expensive redesigns, remanufacturing, significant penalties. Not because their product is actually bad, but because the test itself is inherently biased against them.
Wow.
It's mathematically equivalent to unknowingly setting a much higher target MTBF than what was declared in the contract. So using this type of test can be very detrimental for the supplier. It should generally be avoided unless all parties fully understand and explicitly accept these implicit asymmetrical risks. It's a fundamental statistical fairness issue.
That's a huge warning. Okay, reliability is key, but it's only one piece of the puzzle, isn't it?
Absolutely.
For our high-speed rail, what about whether the system is actually available when needed, ready to carry passengers?
Yes, availability, crucial.
And how easily can it be fixed if it does break down? Let's dive into availability and maintainability. Just as critical for a functioning, on-schedule railway. A reliable train sitting broken in the depot doesn't help anyone.
Couldn't agree more. For complex systems like railways, contractual commitments on availability levels are incredibly common, and they have direct financial implications.
Penalties for downtime.
Significant penalties, often. Clients require a certain percentage of uptime for the whole system, or critical subsystems. This means you need two things. First, accurately estimating availability from operational data. Second, actually demonstrating that target has been reached, often with limited data because you can't wait years for enough failures.
Right.
The challenge here is that, compared to the well-established tests for reliability and maintainability, existing methods for demonstrating availability of a repairable system in continuous operation are still, well, somewhat incomplete is the technical term, less mature.
Harder to prove. Why?
It's harder because availability factors in both how often something fails and how quickly it's fixed. Two different types of events influencing one metric.
Okay, so how do we demonstrate availability for a complex system like a high-speed train? Are there specific methods?
Yes, there are a couple of approaches. One method is an availability demonstration test. often used when you can assume constant failure rates or maybe Erlangian distributions for failure-free and repair times.
Or the mean.
It's a specific type of probability distribution. The goal here is to demonstrate the asymptotic and steady state availability.
Meaning the long-term average.
Exactly. The long-term stable availability percentage the system should achieve once initial teething problems are sorted out. Or, more practically, we demonstrate its complement, unavailability, 1 minus availability.
Okay.
We set up hypotheses similar to reliability. Null hypothesis, H, is that true unavailability is less than or equal to a specified target, PA, or say 1%, meaning 99% availability.
Target availability.
Alternative hypothesis is that true unavailability is greater than a maximum acceptable level, PA, or say 2%, meaning less than 98% availability.
Minimum acceptable.
And just like before, there's an allowed supplier's risk, alpha, of rejecting a good system, and an allowed client's risk, beta, of accepting a bad one.
Alpha and beta again. And how does that test procedure work in practice, say, for the train control system?
Okay. For a given PA arrow and your risks, alpha, beta, you first find the smallest integer n. This n is related to the number of failure-free times and repair times you need to observe.
The sample size.
Essentially, yes. It's calculated using specific quantiles of the F distribution values from a statistical table that help determine the sample size based on expected variability in uptime and downtime.
Okay.
Then, a limiting value, delta, is calculated. The test involves observing in failure-free times and their corresponding repair times. The system is rejected if the ratio of the total repair time to the total failure-free time is less than or equal to delta. Accepted if it's greater.
What's fascinating here is it sounds like you're essentially comparing the total downtime versus total uptime ratio against a threshold.
That's the core idea, yes.
But the major practical problem you mentioned earlier, I imagine it has to do with how long this takes for a high-speed railway.
Exactly. Unlike fixed reliability tests, the test duration for availability demonstration is not fixed in advance.
Ah, there it is again.
This can pose a significant challenge for real railway project timelines, which are often very tight. You might not know if your system will pass or fail until a potentially very long observation period has elapsed.
Making planning difficult.
Extremely difficult. Imagine telling investors the launch date is TBD because the availability test isn't statistically complete.
Yeah, not good.
This method can be generalized if failure-free and/or repair times follow that Erlang distribution, which is a sum of exponential variables.
So if you can't assume those specific distributions, which must often be the case with real-world, messy data, what then?
That's where the second method comes in. Confidence intervals for availability, using the Chebyshev inequality.
Chebyshev, okay.
The advantage here is that this method is far more general. It doesn't require specific assumptions about the underlying distributions of uptime or repair times, only that they are independent.
More flexible.
Much more. It models the process as an alternating renewal process cycles of uptime, followed by downtime, repeating. This is incredibly useful for a complex system like our train, where downtime might have mixed causes and repair times vary wildly. A simple exponential assumption might be unrealistic.
How does it work?
It uses the mean and variance of the total downtime observed over a specific time interval t to derive a confidence interval for unavailability. This provides a more robust way to estimate and potentially demonstrate availability without relying on potentially incorrect, restrictive assumptions about the data's distribution.
Okay, that makes sense. Reliability tells us if something breaks. Availability tells us if it's ready to use. But what about getting it back up and running quickly?
Maintainability.
Right. So what does this all mean for how quickly a high-speed train can be fixed if it breaks down mid-journey, minimizing delays for passengers? That's where maintainability demonstration tests come in.
Exactly. Maintainability tests have two key objectives.
Sure.
First, and often most important contractually, they aim to demonstrate the achievement of targets for repair times.
Like MTTR.
Yes. Maybe a maximum mean time to restore, MTTR, for the whole train, or a mean active corrective maintenance time, MACMT, for a specific component that's the average time spent actively fixing that component.
Okay, MACMT.
For our high-speed rail, a short MACMT for a critical component means less downtime, fewer delays.
Makes sense. And the second objective?
Second, these tests are crucial for verifying qualitative aspects. Things like the adequacy of the test support documentation. Do the manuals actually help a technician in the field?
Good point.
And the overall ease of maintenance. Is the system designed to be easily accessible, diagnosable, repairable?
So not just how fast, but how easy.
Precisely.
And the scope of these tests is broad, isn't it? It's not just about the tech repair crew.
That's absolutely right. These tests consider both corrective maintenance, fixing broken things, and preventive maintenance routine checks and servicing, like inspecting the train bogies. And crucially, they sometimes even include tasks performed by operational personnel, like train drivers, who might need to do basic resets or checks on board that impact service recovery time.
Interesting. Who actually conducts the tests? Supplier? Operator?
That's an ongoing discussion, actually. Some argue supplier personnel should do them to isolate the intrinsic maintainability of the equipment from how well the client staff are trained.
Isolates the design factor.
Yes, but if suppliers conduct them, it's paramount to ensure their personnel are well-trained and follow realistic procedures to give a true reflection of what the railway operator's own technicians will experience.
All right, needs to be realistic.
A beautifully designed system that's a nightmare to diagnose or physically access will quickly erode its perceived reliability in operation.
So there's an assumption made about the distribution of these maintenance times for the stats. You mentioned the log-normal distribution hypothesis.
Yes, it's a very common and practical assumption in maintainability testing. It's typically assumed that the probability distribution of active corrective maintenance times follows a log-normal law.
What does that mean in simple terms?
It means that while the maintenance times themselves might not follow a neat symmetrical pattern, some fixes might be very quick, but a few could be extremely long, creating a long tail in the data.
Skewed data.
Right. But the logarithm of those maintenance times does follow a normal bell curve distribution, usually with a known variance.
Okay.
This is great because it allows us to use powerful statistical tools developed for normal distributions to analyze maintenance data, even when the raw repair times are skewed.
Handy. Now, how do you actually run the test, say, for our high-speed rails pantograph system?
Okay. There are two primary scenarios. If you expect a statistically significant sample of actual failures to occur naturally during your demonstration period, maybe for wear and tear items,
right,
you can perform random sampling from those real failures. However, for systems with very few components or highly reliable items like a critical control unit that rarely fails.
You can't wait forever.
Exactly. Waiting for enough real failures isn't practical or timely for a tight project schedule. In such cases, it becomes necessary to conduct failure simulations.
Simulate the breakdown and repair.
Yes. The good news is that the same statistical methods that apply to random sampling of real failures can still be applied when you're simulating them, provided the simulations accurately reflect real-world scenarios and repair conditions.
Okay, so how do you design one of these maintainability tests for a crucial component on our train? What are the steps?
Okay, assuming the log-normal distribution and a known variance of the log of maintenance times, the procedure generally follows these steps. First, you determine the minimum sample size N.
Calculate N.
Yes, it's calculated using the producer's risk, alpha, consumer's risk, beta, the assumed variance of the log of maintenance times, and the target and acceptable MACMT values.
Alpha, beta again.
Always. Critically, this sample size must be at least 30.
Why 30?
It's a statistical rule of thumb for the central limit theorem to apply. This allows us to assume that the sample mean of the maintenance times, regardless of individual times, will follow a normal distribution. This simplifies the analysis and ensures robust results.
Okay, need at least 30 observations, then you collect them for, say, a braking system component.
Exactly. Step 2 is to collect observations of the active corrective maintenance times, ACMTs. For that component, the measured repair times.
Measure the repair time.
Third, you calculate sample statistics from these observations, specifically the sample mean and the sample variance.
Average repair time, basically.
Yes. Finally, you apply the acceptance rule. The core of this rule is whether the calculated sample mean of your observed maintenance times is less than or equal to a predefined threshold. This threshold depends on your target MACMT, the producer's risk, alpha, and the calculated sample variance. If your observed average repair time is below that threshold, you accept the hypothesis that the system meets its maintainability target. Otherwise, you reject it.
Okay. Clear pass-fail based on the average repair time. But this raises an important question. If you have a complex subsystem like the entire propulsion unit of a high-speed train made of maybe dozens or hundreds of different parts, line replaceable units, LRUs.
Yes, many LRUs.
How do you decide which ones to test for maintainability to get that sample size in? You can't test every single LRU 30 times for every single type of repair.
That's a very practical challenge, absolutely. And it's where strategic thinking comes in. One common and effective solution is to break down the required total sample size among the different LRUs based on their respective failure rates.
Based on how often they fail.
Exactly. The logic is quite simple and powerful. Items that contribute more to the subsystem's overall failure rate should logically be tested more times for maintainability because, well, they are expected to fail more often in the field.
Makes perfect sense. Prioritize the troublemakers.
Precisely. So if your overall propulsion unit needs, say, 43 maintainability tests across all its LRUs, and one specific LRU, like the inverter module, contributes 35% of the unit's total expected failures, then roughly 35% of those 43 tests, about 15 tests, should be conducted on that particular inverter module. Meanwhile, a highly reliable LRU that rarely fails might only get 1 or 2 tests.
Focus the effort where it matters most.
Exactly. It's about prioritizing testing effort, where the highest impact on overall system maintainability and operational efficiency is expected, ensuring you get the most relevant data.
Can you walk us through a quick numerical example, just to see how these numbers might work for a specific component's MACMT?
Certainly. Let's say we want to demonstrate a mean active corrective maintenance time, MACMT, target of 1.75 hours for a DIC and, let's say, a critical sensor in our trackside signaling system. We'll call this target mu0.
1.75 hours targeted. Okay.
And we also have a maximum acceptable MACMT from the operator's perspective of 2.25 hours. Let's call that mu1.
2.25 hours max acceptable.
Let's set both the producer's risk, alpha, and the consumer's risk, beta, at a reasonable 20%, or 0.2, meaning we're allowing for a certain level of acceptable uncertainty for both sides.
Okay, 20% risk each.
And based on historical data or expert judgment, let's assume the variance of the logarithm of maintenance times, sigma squared, is known to be 0.5.
Variance of 0.5, got it.
Okay, given these parameters, we can first determine our minimum sample size n, using the relevant statistical formulas for A and B of 0.2. The corresponding standardized normal deviate z is approximately 0.84.
Okay.
When you plug these values into the sample size equation, you'll find that n works out to be exactly 30.
Oh, perfect. Meets the requirement.
Yes. Confirms we meet the central limit theorem requirement, allowing us to use a normal distribution for the sample mean. So for this sensor, we need at least 30 observations of active corrective maintenance times.
And once we've collected those 30 observations, what's the actual acceptance rule for that sensor? How do we know if it passed?
Right. Once you've collected those 30 observations and calculated their sample mean x bar, the acceptance condition is straightforward. You accept the maintainability target if your calculated sample mean x bar is less than or equal to a specific threshold.
Calculated threshold.
Yes. This threshold is calculated using the target MACMT, 1.75 hours, the Z value for your producer's risk, 0.84, and the known variance, 0.5. In this specific example, the threshold would be approximately 1.97 hours.
Okay, 1.97 hours.
So if the average of your 30 observed repair times for that sensor is 1.97 hours or less, you accept that the system meets its maintainability target.
And if it's higher?
If it's higher than 1.97 hours, you reject it. This provides a clear, statistically sound basis for demonstrating maintainability, ensuring that our high-speed rail systems can indeed be fixed quickly when needed.
Okay, that makes it very concrete.
What's fascinating here is, and this is really a key point, every RAM demonstration test we've discussed today, whether it's for reliability, availability, or maintainability, inherently includes a notion of risk, both for the producer who designed and built the system and for the consumer who will operate it.
Alpha and beta. Producer and consumer.
Exactly. It is absolutely critical not to neglect these risks. If you do, you could easily find yourself facing unfair and incredibly costly contractual obligations. Or worse, accepting a system that simply won't perform as needed, leading to delays and safety concerns for our high-speed rail.
So just comparing an average to a target isn't enough?
No. The seemingly naive method of just comparing a point estimate, like an average observed MTBF, to a target, without accounting for these statistical risks, it just doesn't capture the whole picture. It can lead to very poor and very expensive decisions.
That's a crucial takeaway then. True demonstration tests must be meticulously designed, balancing the very real-world constraints of time and cost, especially for a project like high-speed rail with rigid launch dates.
Always tight schedules.
With the statistical need to minimize test duration and, crucially, minimize the risk of making a wrong decision. It's a really fine line to walk.
It really is, especially in complex, high-stakes environments like railways. It's about building trust, but doing it intelligently.
Yeah.
And the perpetual challenge in railway projects is that they always operate on incredibly tight program schedules. Demonstration periods are typically short, sometimes only a few months to maybe a couple of years.
Not long for complex systems.
Not at all. This presents a huge challenge, especially when you're dealing with highly reliable products, like modern high-speed trains that rarely fail.
Right, you need failures to measure reliability.
Exactly. It simply takes a long time to observe enough failures to be confident that the targets are met with statistical significance. This immense time pressure is often what explains why incorrect testing methods, like that problematic chi-square confidence interval method we talked about,
The biased one.
are sometimes proposed. They seem to offer a quicker path, but at a hidden cost of increased, often asymmetric risk to one party.
But there are solutions, right? It's not all doom and gloom. Beyond sequential tests, you mentioned something else.
Yes, another powerful alternative to get insights faster and dramatically reduce testing time is accelerated life testing, or ALT.
Accelerated life testing, ALT. What's that?
This involved intentionally increasing stress on a product. Think higher temperatures, more operational cycles per hour, increased voltage, simulated harsh environments.
Pushing it harder.
Exactly, to accelerate its time to failure. By understanding how the product behaves under these accelerated conditions, engineers can extrapolate its performance under normal operating conditions.
Predict normal life from stressed life.
Precisely. Gaining reliability insights much faster than waiting for failures under normal operating conditions. It's about compressing years of potential operation into weeks or months, allowing you to validate a design for our high-speed rail even before all the physical infrastructure is complete potentially.
That sounds incredibly useful.
It can be. And that leads to maybe a provocative thought for you, our listener, to consider.
Okay.
As railway systems become even more complex, increasingly reliant on software, automation, maybe AI, even heading towards autonomous operation.
Yeah, the future.
How will RAM demonstration continue to evolve? What new challenges will arise in proving the reliability, availability, and maintainability of truly autonomous trains or next-generation signaling systems that are largely software-defined?
Good question.
What stands out to you as the most surprising or impactful insight from this deep dive into RAM demonstration in railway projects today?